Say I tell you that diamond is an insulator, copper is a conductor and silicon is a semiconductor. This is as far as their ability to conduct electricity is concerned. Now immediately your question is going to be, but how do you know that? Are there any values that you have measured on the basis of which you can justify your claim that copper will conduct electricity and diamond will not conduct electricity? And my answer to that would be yes. Now these are the values that we are looking at: the resistivity, the temperature coefficient of resistivity and the number density of charge carriers. You know that the resistivity rho is found from the resistance R is rho L over A, and if you compare the resistivity, then resistivity for insulators is extremely high. Metals have a very small value of resistivity and semiconductors have a resistivity which is considerably higher than that of metals or conductors. For instance, if you would look at copper, copper has a resistivity of about 2 into 10 to the power minus 8 ohm meter, and the value for silicon would be 3 into 10 to the power 3 ohm meter. And if you look at the resistivity for diamond, diamond is almost 10 to the power 24 times the value that you have for copper. So the resistivity for diamond or an insulator is extremely high. Now if you're going to compare the temperature coefficient of resistivity, let's first define the temperature coefficient of resistivity, which is denoted by alpha. Alpha is equal to rho dash minus rho naught upon rho naught times T dash minus T naught, where T naught is a reference temperature and rho naught is the resistivity at that reference temperature. Now if you're going to compare the temperature coefficient of resistivities of metals and semiconductors, you find something very interesting. In case of metals, the temperature coefficient of resistivity increases with the rise in temperature, whereas in case of semiconductors, the temperature coefficient of resistivity is negative. It actually decreases with the increase in temperature, which means that at higher temperatures, semiconductors conduct electricity more easily as compared to lower temperatures. So the number of charge carriers seem to increase if the temperature is high in case of a semiconductor, but in case of a metal, at higher temperatures the resistivity is more, because the disorder within the metal increases, the number of collisions become more frequent, so the resistivity increases with the rise in temperature. Now values for, if you compare these values, for copper we'll have a value of about 4 into 10 to the power minus 3, and the units would be per Kelvin, and for silicon we have a negative value which is minus 70 into 10 to the power minus 3 per Kelvin. Now the last quantity N is the number of charge carriers, and as you would guess, the number of charge carriers in a conductor is extremely high if you compare it with the number of charge carriers in a semiconductor. For instance, the number of charge carriers in copper would be 9 into 10 to the power 28 per meter cube, whereas in case of silicon the number of charge carriers would be 1 into 10 to the power 16 per meter cube. So you can see that the number of charge carriers is much higher in case of a good conductor. See, all these three values can be measured experimentally, but there is still another feature that is used to distinguish between insulators, conductors and semiconductors, and that is the energy band structure. So now we look at energy band structure in crystalline solids. See, when we are talking of crystalline solids, we are referring to solids whose atoms are arranged in a repetitive three-dimensional structure which is called a lattice. Example, copper could look something like this, and this would be for silicon and diamond. Now these lattices that I have drawn over here are just representative, so for an exact diagram please refer to a book. Now in solids like wood, plastic, rubber etc., the atoms are not arranged like this in repetitive patterns. Now, if you think of a single isolated copper atom, it has 29 electrons, and these electrons are distributed among a set of subshells. And the distribution can be written as 1s2. Now, I've drawn these subshells over here, and for simplicity, I've just drawn them equally spaced. And you can see that the 4s subshell has only one electron in it and can actually accommodate 2 electrons. And the higher subshells are also empty. This point that we just mentioned is going to be important in determining the conductivity of copper. Now, if 2 atoms of copper are brought close together, so now instead of 1 atom, we have 2 atoms of copper, then it is as if one atom can sense the presence of the other, and we need to take this interaction into account. So the outermost or the valence electrons are affected the most, and the inner electrons are going to be the least affected. Now, in quantum mechanics, we say that the wave functions of the 2 atoms overlap, and now we can think of it as one single system with 2 atoms which has 29 into 2, which is 58 electrons which need to be accommodated. And to accommodate these 58 electrons, there have to be 58 levels available, and now each of these levels splits into 2 levels. Now say we are bringing more atoms and we finally have n atoms, where n is about 10 to the power 24, which is of the order of the Avogadro number of atoms, which is quite possible. Then each level of the individual isolated atom has now split into n levels. So now instead of energy levels, we have energy bands, as some energies shift a little upward and others a little downward by varying amounts. See, now the individual levels within a band are very close together, and the number of levels is also very vast. Since n is very large, so we can now think of these levels as forming a continuous distribution of energy within a band. If you notice, between adjacent energy levels, there are gaps or forbidden regions where there are no allowed energy levels, and this is called the energy gap. Now, these energy band diagrams can be drawn from metal, semiconductors as well as insulators, and so we'll distinguish between these 3 categories of solids on the basis of the energy band diagram. First of all, in case of an insulator, if you apply a potential difference across the material, no current flows. For current to exist, some electrons must gain energy, or we say that they move to a higher energy level. Now, in case of an insulator, the highest band which contains electrons, you can see, is fully occupied. So there is no place for the electrons to go to. This highest filled band is called the valence band, and the next higher band is called the conduction band. And between the valence band and the conduction band, you have an energy gap. This is called the energy gap. You can see there are a lot of energy levels over here, and these are unoccupied, but to be able to jump this energy gap over here, the electrons require a lot of energy, because in case of insulators, this gap is extremely large. Now, in case of diamond, this energy gap is about 5.5 electron volts, and the energy that the electrons have at room temperature is just about 0.025 electron volts. So you can see that they would need an energy which is about 220 times more than the energy that they have. So it is not possible for the electrons to jump this gap. So there are no conduction electrons available, and the material is an insulator. Now, in case of metals or conductors, the highest occupied level falls somewhere near the middle of the energy band, which means if a potential difference is applied to the metal, a current will exist, because there are plenty of vacant levels which are available over here to which the electrons can jump. So the valence band might either be partially filled, or the valence band and the conduction band might be overlapping, which means the energy gap is zero, and there are once again a lot of empty energy levels available to which the electrons can jump from the lower level to a higher level. So in this case, since there are a lot of conduction electrons available in the conduction band, the conductivity is high. The band gap pattern of a semiconductor is quite similar to that of an insulator, except that the energy gap is much smaller over here. So the electrons, because of the thermal agitation, have some probability of jumping the gap. Now the band gap of silicon is about 1.1 electron volt, and that of germanium is about 0.74 electron volt. Now these electrons that reach the conduction band are free to move and conduct electricity. So with an increase in temperature, there are more electrons which will jump from the valence band to the conduction band and increase the conductivity of the material. Try these questions to test your understanding. The answers are discussed a short while later. The first graph is that of a semiconductor because the resistivity is decreasing with temperature, and the second graph is that of a conductor because the resistivity is increasing with temperature. The energy levels of the inner electrons remain relatively sharp. This is true because the outermost electrons or the valence electrons are affected the most when the electrons move close together. Let's say this is the valence band and this is the conduction band. An electron which is present over here absorbs a photon and moves into the conduction band, and the value is 0.67 electron volt. So this means that the band gap or the energy gap will be 0.67 electron volts, and the material will be a semiconductor because the energy gap of a semiconductor is less than 3 electron volts,